So in the last video, we covered section 4.4 and 4.3, and this was on further properties of the exponential and logarithmic functions. And we're going to continue, as we have been doing, studying functions. In this next chapter, we're in chapter 5, we're going to look at a new class of functions, the trigonometric functions. And we're going to revisit these functions in chapter 6. We're going to give two different but yet equivalent ways of defining the trigonometric functions, and having both pictures in mind is helpful. So today we're going to cover section 5.1, and that's on the unit circle. So we have the unit circle approach to defining functions, and then we have maybe the more familiar approach, the right triangle approach to defining the trigonometric functions. But I think the unit circle approach is kind of, it sort of includes the right triangle approach. So this is maybe a more fundamental way of defining the trigonometric functions. So let me share my screen. Okay, so this is, let's see. So we're in 5.1. And this is trigonometric functions. This is the unit circle approach. Oops. So in order to define these trigonometric functions, we need a new way of thinking, a new way of thinking about the unit circle. So the unit circle is, the usual way of thinking about the unit circle is this object living in the plane. So we have this two-dimensional way of viewing the circle. So the unit circle is the set, I guess this is one way of thinking, the set of all points x comma y in the plane. So r squared, remember r squared is the plane. It's r squared just consists of these kind of ordered pairs. But it doesn't just consist of, the unit circle doesn't consist of just any set of ordered pairs. It's got to be all those ordered pairs such that, ordered pairs x and y, such that x squared plus y squared is equal to 1. So that's the definition of the unit circle. It's all points x and y such that this equation holds. This is what it means for a point to be on the unit circle. So this is like very inherently two-dimensional, but we want a simpler way of thinking about this. So if we just confine ourselves to the unit circle, so the unit circle is just our universe. So we're imagining ourselves on the unit circle. So let's draw that. So let me see, maybe I can never really used this tool right here. Can I draw it? Something like that. So let's say that's our unit circle right there. And I'll just draw on the axes. It's not going to be perfect, but it's the best I can do. So this is our unit circle right here. So now let's think about, like, our universe is no longer this supposed three-dimensional or maybe four-dimensional object, with space and time, but we're just imagining ourselves as our universe is this unit circle. So we're a point on there. If you're on the unit circle, And like, you can't look to your sides, you know, there's no such thing as that. If the unit circle is our universe, points here don't exist really. Points on the inside and points on the outside of the unit circle don't exist from our perspective. So we can only basically look forward and backwards. If that's the case and you move along it, you know, you're trying to march along locally, and this, you remember when I talked about neighborhoods and local behavior, this is all like topology talk. So this is another area of mathematics. I talked about group theory, but I'll also talk about topology. Locally, it looks no different than just walking in like a straight line, right? So like if you just like cut off this piece right here, if you're just like of the circle, if you're looking at this arc and you're like moving it along it, and you kind of stretch it out, it just looks like you're moving in a straight line, maybe forwards or backwards. So locally, it looks like that. And in fact, this is really one way, you know, of topologically viewing the circle. You take the unit interval. So you get this unit interval. And you have the endpoints, and you glue. You can make this notion of gluing really precise mathematically, and you do this a lot in topology. You can glue endpoints of the interval 0 to 1 to get the unit circle. So if you're just moving around on the circle, say we're measuring how far we are from this point right here, 1, 0. We're basically measuring arc length right here. You really only need one number to specify where you are on the circle. So although the circle lives in 2 dimensions, like that's our usual way of thinking about it, really the circle, if you're on it and that's your universe, is really just a one-dimensional object. It's more precisely, yeah, and again, a lot of the stuff you don't need to know, but just for those who are interested, maybe they want to go further in mathematics. The circle, oops, is basically a one-dimensional topological manifold. So you only need, like, dimension roughly means like the number of numbers you need to specify a position in your space. So like in 3 dimensions, you need 3 numbers, you know, like, or so let's say just 2 dimensions more simply. Like if you're in if you just take the whole plane, if you take the whole plane and I give you a point here, you know, generally you need 2 numbers. You need like this number here, I'm drawing, and then this number here. So it tells you how far you need to go along the x-axis, and then how far you need to go along the y-axis here to get to that point. There are a lot of ways you can, these are called the Cartesian or rectangular coordinates. Those are like the really most familiar coordinate system we use, but you can also use polar coordinates, and polar coordinates is like, again, you still need 2 numbers, but polar coordinates specify a point in the plane by telling you the distance from the origin and the angle from the x-axis. But the point is that to specify this position in the plane, you need 2 numbers generally. You need, you know, x and y coordinates to tell you how far to go along the x and y axis, or polar coordinates, which you'll discuss more in calculus, which tell you how far you are from the origin and the angle you make with the x-axis. So dimension roughly means like tells you the number of numbers you need to specify a position in your space, whatever that space is, whether it's 2 dimensions, 3 dimensions, you know, 100-dimensional space, infinite dimensional space. And what we're saying is that the circle, although it's usually thought of as a two-dimensional object living in the plane, really you can think about it like if you're just restricting yourself to points on the circle itself, is just a one-dimensional object, and all you need is really to specify a point uniquely. Yeah, uniquely, you need well, to be unique, you need two you need a positive or negative number. So the convention is that if you're moving along counterclockwise, so you're going this way to this point right here, you use a positive number, so it's like a positive arc length. But if you're going the other direction, you can go this way, and that will be you use a negative number to specify that. But the point is that circle, the way we want to think about the circle is that it's a one-dimensional object. When you restrict yourself just to the circle, it's one-dimensional, and you only need one number, which is basically the arc length, to specify a position on the circle or position on this space. So the space we're thinking about is the circle, and it's really just a one-dimensional object. So if we really get that into our head, it'll make defining these trigonometric functions a lot easier. So let's see. Yeah, so let's just kind of summarize what's going on here. So well, yeah, let's make this a little more precise. So again, we have the unit circle. And we're basically using arc length as our way of determining where we are in this or where we are in the circle, or what point we're at on the circle. So if you go along we're always measuring with respect to this point. It's just, you can measure with respect to any point you want, the arc length, but it's just easier to choose this point right here, 1, 0. And so if we go so because this is a unit circle, if you go all the way around the circle, you've traveled the circumference. But the circumference of the unit circle is just 2 pi times the radius, but the radius is just 1, so it's 2 pi. So any point on the circle, yeah, so I want to say any point on the circle will correspond. There's like this one-to-one correspondence, I guess. Maybe not one-to-one actually, but there's a some sort of correspondence to a number in the interval 0 to 2 pi. So 0 means you didn't move. So like these are our arc lengths right here. 0 means you didn't move. You just stayed at the point 1, 0. You didn't move along you didn't go any distance along the circle. You didn't travel any arc length. 2 pi means you went all the way around. You started here, and then you went all the way around. You traveled this way. So you can use these arrows to indicate like which direction you're traveling. So you traveled all the way around the circle. And then any point between 0 and 1 will mean you traveled some of the distance. So some of these numbers we can actually just determine. So if I travel up to this point, that means, so I've started at 0, 1, and I went to this point. And this point is, because we're in the unit circle, we can deduce that it's actually just 0, 1, because the x coordinate is 0. Since it's a point on the circle, the x coordinate we know is 0 because it's on the y-axis. So that means the only option for the y coordinate is 1, because remember we have to satisfy, to be a point on the circle, we have to satisfy this equation, right? So if x is 0, then that implies y squared is equal to 1, so y is equal to plus or minus 1. But it's clearly on the positive part of the y-axis, so that point will be 0, 1. But the more relevant point is that if we start here and travel to this point on the y-axis, we've gone a quarter of the way. So the whole length, the length of the whole circle, the circumference, is 2 pi. So a quarter of the way means we've gone a distance of pi over 2. So in other words, pi over 2, so the point 0, 1, and I'll put this in quotation marks because it's not an exact correspondence, but the point 0, 1 corresponds to the arc length pi over 2. So now we went from using 2 numbers to specify a point on the circle to just 1 number. We just measure how far along we've traveled, and that will along the circle, and that will give us a point on the circle. So we only need 1 number to specify a point, and we can get a couple other numbers too. So like this number right here. So the point, this point corresponds to -1, 0. And the arc length corresponds to pi, because you went halfway around the circle, right? So you went half of the circumference. So this point right here is pi over 4. This right here is pi, and this right here, will be 3/4 of the way, and so that would be 3 pi over 2. So if you just like multiply 3, you can get these numbers the exact same way. So maybe I'll just, so this is negative, or 0. This is 0, -1. So let me just show you how I got these numbers. So 0, -1 corresponds to halfway around the circle. So the arc length is 1/2 times the total arc length, though the circumference of the circle, so it's just pi. That's how I got pi for this point right here. And then the other one is, sorry, this is not right. This should be -1, 0. -1, 0 corresponds to pi. So, and then if I start at 1, 0 right here, and I travel all the way around to this point right here, 0, -1, that will correspond to 3/4 of the way, I should say, of the way. So of the way around the circle. So the arc length corresponding to that the number that specifies that point, instead of just dealing with 2 numbers, we want to deal with 1 number, corresponds to 3/4 times 2 pi. And the factor of 2 will cancel that 2, so we get 3 pi over 2. So these are some numbers you want to remember. Now, this correspondence isn't unique though, because if I go around the circle, so we only care about position, not how far we're traveling. If we were maybe physicists, we would care about that, because say if you're on the circle and like there's an electromagnetic, so suppose you have a charged particle traveling around the circle and there's an electromagnetic field, and maybe the electromagnetic field has different strength on different points of the circle, then we would care about how far you're traveling, because we would maybe want to know something like, well, what sort of energy do I need to put into the particle? How do I need to accelerate this to make it around the circle? Because it's, depending on the electromagnetic field, it might slow the particle down, the charged particle down. So in that case, we would care about suppose what we call displacement, like how far you traveled, or no, distance. We just care about displacement. That is, where did we end up? We don't care about how far we traveled, just where we end up. And that's where this correspondence breaks down a little bit, because suppose you travel around the circle twice. That means you traveled an arc length of 4 pi, but 4 pi really just corresponds to that same point. So in some sense, we have a bigger number than we need. So we want to talk about a reference number. So this is where the correspondence breaks down. We need to talk about a reference number, because sometimes these numbers get too big and it's hard to determine what point we're talking about. So maybe I'll give you an arc length and you have to determine the point on the circle. Well, it's hard because it might be a very big number and we need to reduce it in some sense. And I'll explain that in more detail. But the point is that you can go around the circle as many times, you can wind around it as many times as you want, and then you're traveling a very large distance, but you might land at the same spot point, for example, and so you didn't travel, you didn't change your position, and so the arc length will be should be a smaller number. So let's look at, before we do that though, let's look at some more of these values. So I gotta stop sharing my screen, hold on. Let's look at more points on more points on the x-axis. So I'm gonna pull up, or not, the more points on the unit circle, sorry. So we have these points, yeah, so when you travel along the circle, you determine a point in the plane, which is specified by 2 numbers, but we want to exchange that. So here's the point 10. That's like our reference number. That's our reference point. That corresponds to I think they call it not sure what they call it. I guess just arc length, I guess how you would call it. So this reference point is 10. That's the point right here. And that corresponds to this number 0 because you didn't travel. And then you have these other points. So pi over 2, that's one we looked at just a moment ago. That's 0, 1. That's when you travel from 10 and you travel a quarter of the way to 0, 1. That corresponds to traveling pi over 2. And then you have these other ones. These are important to remember too. So you have, as you travel along, if you stop here, it determines a point in the plane. That point is square root of 3 over 2, 1/2. And you can, there's a proof that this corresponds to pi over 6. I won't go through the proof. You can look in the book. I think they give you a proof. But when you travel this length, when you travel to this point on the circle, it corresponds to an arc length of pi over 6. So that's that distance right here. Let's see if I can, oops. So you've traveled from here and it went up to, it's not working. Oh. So you traveled here to here. and that will correspond to pi over 6, and then you can travel from here to here along, going along the circle. It's not the straight line. That will give you pi over 4, and then you can travel from here to here. So that will give you the point 1/2 square root of 3 over 2, and that corresponds to an arc length of pi over 3. So these numbers look scary, but they're not. Notice they're just like these ones. Eventually, like you'll figure out these numbers. Notice they're just swapped. So the way I remember, like, why does this point correspond to this angle or this this arc length, and why does this correspond to that? Well, another way of thinking about this is like, well, this number right here is smaller, so you've traveled less along. You've traveled less than you would if you traveled pi over 3. So that means that your x coordinate should be big, because like if you drop down right here to your x coordinate is big, but this point right here, if you drop that down here, x coordinate is small. So how I remember how these points link up is I say, okay, well, pi over 6 is smaller than pi over 3. So that means I travel along a shorter way along the circle. So that means my x coordinate should be bigger than my y coordinate. And that's how I remember. And notice they're just swapped, the coordinates. So a lot of these points will look similar. Okay, so that's the table. Those are some numbers you're going to want to remember. And then all other points will basically, you can deduce it from there. So let's see. Let's look at an example. So this is example. This is example 3. We have, so the question asks us to find the terminal point on the unit circle determined by or corresponding to by, and this is part A, t is equal to 3 pi. So this represents an arc length. We start at the point 1, 0, and then we're going to travel around the circle. And we want to know what point that determines in the plane. So we're just trying to get better at like going back and forth between these two ways of viewing the circle, as a 2-dimensional object and as a 1-dimensional object. So let's draw our unit circle. Let's see. No, I don't like that. So this number can be written as 2 pi. So distances are additive, right? If I travel, so I can, this represents an arc length, distance I traveled. So distances are additive. I can write, if I travel 3 pi, that means I can, for example, view that as meaning I traveled 2 pi, and then I traveled pi, distance of pi. Well, if I traveled 2 pi, that means I go around the circle. So that would correspond to this piece right here, the 2 pi. But now I'm going to travel pi again. I'm going to travel another distance, pi. So that means I go halfway around the circle. So the point corresponding to this, so this corresponds to the point 0, -1, right? So that corresponds to 0, -1. So let's look at another example. So This is an example of when we travel in the opposite direction. So positive numbers means you travel counterclockwise, negative numbers mean you travel clockwise. So we have, the arc length we have, or this real number, this number we have is pi, negative pi, and we want to determine what point that corresponds to. So this time we travel in the opposite direction. Well, if we look at the size of the number, that is the absolute value of the number, that's going to tell us how far we travel. And if we take the absolute value of this, so the absolute value of t is pi. So that means the distance we're traveling is pi, and the direction is clockwise. So we travel pi, and that's half the circle. So we end up at this point right here. So this point is the same as we determined in the other one. So this shows that this correspondence between these arc lengths are signed arc lengths, because we can look at positive numbers and negative numbers, and they'll determine whether we travel one direction or not. This correspondence isn't quite unique, because I have two different t values. I have a positive value and I have a negative value, and they both determine the same point on the circle. So here you have to be careful. So maybe this is the trade-off of viewing the circle as a one-dimensional object. You do have to be careful about the point you're looking at. Is it do these numbers determine the same point or not? But that isn't usually too bad. It isn't usually too difficult to determine. And let's look at the last part. So we have that this number that we're looking at is pi over 2, and that means we travel clockwise along the circle, and that's going to determine a point on the circle. So first of all, the absolute value of t is pi over 2. So that's true. So that will tell us the distance we travel, not the direction. It will just tell us the distance we travel. So we have our circle. Now, if we just look at pi over 2, that means we have to travel. We travel a quarter of the way. That will give us this point, right? 0, 1. But now we're going to go negative, so it's kind of the opposite point. So that will tell us that we have to travel this way. The negative sign means we travel this way, and we end up at this point. But these points are like antipodal. They're like opposites of each other. So they only differ by a sign. So the point corresponding to this number is pretty easy to determine. You just put a negative sign. You just multiply by -1. You multiply each coordinate by -1. So this is the point corresponding to t is equal to -pi over 2. Notice this point is also, if we determined above, if you're going counterclockwise, this point is also determined by 3 pi over 2. So again, this number is different right here. This number right here, that's different than the number we just looked at, -pi over 2, but yet they determine the same point on the circle. Okay. So let's look at, so these are some pretty basic ones. These are basically traveling a quarter of the way, or half of the way, or 3/4 of the way. What if we travel at some different fraction, another fraction of the way? So this is example 4 in the book. So the first part, so again, we want to find the terminal point. This question, the setup of the question is the exact same as the one we just looked at. We want to find the terminal point on the unit circle determined by a given point or by a given number, which corresponds to like an arc length, that a distance you travel around the circle. So part A is the following. We're told that we travel a distance of pi over 4. So this is when we're going to need to remember those values. These are the ones that are a little trickier to deduce. We need to memorize the table. So let me pull the book back up. So we're looking at pi over 4. So that corresponds to the point root 2 over 2 and root 2 over 2. Notice this one's easy to remember. Actually, when you have pi over 4, it means both the x and y coordinates are the same. So that's the easy one to remember. So if you look at pi, or if you look at the absolute value, just the absolute value, that corresponds to the point root 2 over 2, root 2 over 2. But the point that we're interested in, though, is going to be some variation of this point. It's maybe the x coordinate has to be negative, or maybe the y coordinate, or maybe both coordinates have to be negative. That we will determine in a moment. But we always want to we want to take the absolute value. It's a good idea to first take the absolute value and look at the point in the circle corresponding to the absolute value, because that will help us determine the point corresponding to the original number. So let's draw our unit circle. Oops. So if you travel, so pi over 4 means you end up like halfway in this quadrant, right? Like halfway between this point and the starting point. So the negative sign means you have to travel in the opposite way. So that means that we should end up halfway in this quadrant too, right? Oops. So this right here corresponds to traveling pi over 4. And that corresponds to the point root 2 over 2, root 2 over 2. This, if we travel in the opposite direction, though, we have to end up halfway in this quadrant. I don't know if that's the exact way. That's actually right to say. Like, I guess just halfway between this point and the starting point. So the coordinates are going to be the absolute values of the coordinates are going to be the same as this point right here. It's just a matter of determining the sign. So when you're in this quadrant right here, when you're in the fourth quadrant, notice the x coordinate is positive, but the y coordinate is negative. So what that means is that this point is going to this number, this distance you travel along the circle in the clockwise direction, is going to correspond to root 2 over 2 negative root 2 over 2. So the only difference between this is that the y coordinate becomes negative. So once you know, so the point though is that once you know there's these 4 points in this first quadrant. There's the starting point, there's this point right here. You need to know this one. That one's easy to remember though. But once you know this point, then there's the point right here and the point right here. You know the coordinates of those points and the numbers corresponding to those points, you can deduce the rest of them. So make sure you memorize those points on this unit circle in the first quadrant. Remember their coordinates, and remember the numbers, those arc lengths corresponding to them, and then you'll be able to deduce any the coordinates of any other point on the circle. So I won't go over part B and C, but they're pretty similar. You play the same game. You look at the absolute value. You look at the point determined by that number, by the absolute value in the first quadrant, and then you ask yourself, okay, well, where does that put me when I look at the positive number? Where does that put me on the rest of the circle? So let's look at the next thing. So this goes back to something I was saying earlier about multiple points determining the same, or multiple numbers determining the same point. And so we want to be able to like reduce these numbers in a sense. So we have the simplest, we have everything is simplified. And we do that using this notion of a reference number. So a reference number, so this is a definition of a reference number. So we say let t be a real number, so t is some real number, then the reference number t bar, so we're going to call this so given t, we can associate this reference number t bar is the shortest distance along the unit circle between the terminal point determined by t and the x-axis. So remember, the terminal point is the point on the circle that you end up at. So I give you this number t. It represents like an arc length in some sense, and you travel along the circle, and you end up at a point, and that point is a point in the plane. So remember, points on the circle are also points in the plane, and that's the terminal point. So, let's illustrate what this reference number is. So we have Struss unit circle. Oops. And so suppose I'm given some t, and let's just say for simplicity it's positive. So that means I start here at 1, 0. I travel some distance, and say oops, crap, I had to do the whole thing over again. Say I end up here. So this whole like wiggly line right here represents the number t. So I traveled that distance, but then what t bar represents is this distance right here, this arc length right here. This is t bar. So remember, so t bar is the shortest distance along the unit circle. So it's going to be you're measuring part of the circle. That is so the reference, this is the shortest distance along the unit circle between the terminal point determined by t. So right here is the terminal point, some point x and y, and the x-axis. So in this case, the arc length is going to be equal to, or the reference number is going to be equal to this little arc length right here. If we were in this situation, suppose T was a number that landed you like right here, the arc, so this corresponds to x comma y, and that corresponds to t. This point is closest to this point on the x-axis, not this point. So this right here, this would not be t bar. In fact, the arc length that you're measuring, t bar would refer to this arc length right here. So in this case, t equals t bar. So they're the same in that case. So this right here is not the shortest. This right here is not the shortest distance to the x-axis. It's this one. So you got to be careful. Sometimes t and its reference number equal, and sometimes they are not equal. Let's look at one more example. Actually, let's see, they have an example with some real concrete numbers. So this is example 5, or yes, example 5. Let's do, hold on. Okay, so we'll do part B and part C of example 5. So part B, in part B, we're given the number 7 pi over 4. And we want to determine t bar. So because we have this 4 here, that means we're going to be in some halfway point in a sense. We're going to be some halfway point. What I mean is, let's just take this graph right here. Remember just pi over 4, it corresponded to, like, this almost looks like halfway. Pi over 4 corresponded to this halfway point. So when you see something pi over 4, know that it's going to mean maybe this point, this halfway point, or this halfway point. It's going to be one of those. And it's a matter of just comparing this number to well-known numbers. So like the well-known numbers are these like points that divide the quadrants. So you have this is pi over 2, this is pi, this is 3 pi over 4, and this is equal to 0, which is like in some sense equal to 2 pi. Because remember what I said at the beginning, to get the circle, you take the interval. You can take 0, 1, or you can also take 0, 2 pi. And you're, sorry. You can take these 2 points and you can take the interval, which is like a straight line, but then glue the endpoint. So what you're doing is, in a sense, you're identifying 0 and 2 point. You're saying they represent the same point. And that's like really what's going on topologically. Like you're to glue those 2 points together, you have to declare that they're the same. And this idea of declaring they are the same is actually not, it may seem weird, like you're saying 2 numbers are equal even though they ordinarily are not, but you do it all the time. For example, when you look at a clock, for example, 13. So if you go all the way around, let's see if I can do my clock right. I'm terrible with arithmetic. So 13, when you do arithmetic clock, so what you call clock arithmetic, you basically, if a number is over 12, you reduce it by 12. You subtract off 12. But what you're really doing is you're just saying like 13 equals 1. So like that would be 1 p.m. So this is, you're identifying these numbers. You're saying that they represent the same thing. That's what's going on with this. And you can look at these. This is called modular arithmetic. So you can look at this set. I won't go into it. Let me see. For those who are interested, what's going on like right here? Let me just write it. Modular arithmetic, and this is stuff you do in group theory. It's very important. So like, for example, you can look at a group, let's say Z mod 6Z. Well, this is going to consist of, so basically what you're saying, every multiple of 6, all multiples of 6 are the same. So you take the integers and you're like deleting all these points. So all you're left with are 1, 2, 0, 1, 2, 3, 4, 5. And then when you add that, and then you can add these numbers, so it gives a group structure. You remember, a group is a set with an operation, and you can add them, and you have rules. Like, for example, 3 plus 4 is equal to 7, but because we're reducing everything, what we call, well, as we say, mod 6, this is really just equal to 1. In the same way that you do clocks. So like clock arithmetic is based on this group, Z mod 12Z. That's clock arithmetic right here. That's what you're doing. Like you want to know what time it is. Well, you add these times together, and then you just reduce everything mod 12. And the same thing same way we did here. But then you also get weird things like 3 plus 3 is equal to 6. Now I got to reduce it 6, so it's 0. So 3 plus 3 equals 0. So you get some weird stuff going on. So this is what's going on. It may seem weird that we're going to glue 0 and 2 pi together and say that they represent the same point. But if you do arithmetic on clocks, which most of us do when we need to keep track of time, you're doing that exact same thing. So this shouldn't be weird at all. It just seems weird at first, but you do it on a daily basis when you keep track of time. So that's why we can say 0 and 2 pi represent the same point, because they, in this weird framework that we're working in where we're identifying points, they do represent the same point on the circle. And so what we want to do for this particular point is we want to know, sorry, I haven't had my tea yet. So as I said, the denominator is 4, so it's something pi over 4, 7 pi over 4. So that means it's going to be either this point here, it's going to be like a halfway point. It's going to be this point here, it's going to be this one here, or this one here. And how we determine what exactly what point it is we compare it to these, I don't know what you call them, like the points that divide the quadrants. So 2 pi, so this number is certainly less than 2 pi, right? So it may be, that means it could be maybe, well, it could be any one of these points really, but what that means is it's not some big number that pushes us over right here. So we have that much is true, but we also have that 3 pi, and you can, if you do, you can maybe in a calculator, you can see this. 3 pi over 4 is less than 7 pi over 4. And that's not hard to see if you, this is if and only if you multiply both sides by 4, you get 3 pi is less than 7 pi. This is certainly true, right? 3 pi is less than 7 pi. So that means this is true right here. So what that means is that t is, t is between 3 pi over 4 and 2 pi. Well, that means that it puts it in this part of the circle, this part of the circle right here. And therefore it has to be this point right here. But what is that point? Well, that means it corresponds to the point root 2 over 2. The x, remember, in this, when you're in this quadrant, the x coordinates are positive, but the y coordinates are negative. So this t value right here corresponds to this point in the plane. Now we have these two different distances right here. So this is the point we're interested in right here. We have this point right here. We have two lengths to the x-axis. We have this one right here. Let me do this in red. We have this one right here. But then we also have this one right here. This one's clearly the smaller one. So this, by definition, is the reference number. How do we get that? Well, we just subtract off the number corresponding to this point and from 2 pi. And that will give us that distance right there, that little arc length. So 2 pi, I'm sorry, t bar will be 2 pi minus, what is it, 7 pi over 4. And if you do that, I won't go through the arithmetic because I'll probably screw it up. I'll just write down what the answer is. It's pi over 4. And that makes sense. That's what that represents is the real, like, if you don't care about the directions you're traveling in, you just care about where you end up. To get to this point, you really can just travel pi over 4 in this so-called negative direction. So those 2 points determine the same. Those two numbers, 7 pi over 4 and negative pi over 4, or just pi over 4, determine the same point. Okay, so let's do one more example and then we'll call it a day. So this is part C. And in part C, we have that t is equal to negative 2 pi over 3. So that means we travel in the negative direction, which is clockwise. So let's draw our unit circle. So to do this, we have to compare our number to known numbers again. Like these, it's going to be between these points, not necessarily these points, but we have these 4 points that are like our, I don't want to say reference point because this is at the actual reference point, 0, 1, but these 4 points are like our comparison points. How about that? So we have a reference point. Let's like fix some terminology here so we're not confused. We have this reference point. That's the point from which we measure all of our arc lengths, and then we have these comparison points, which will help us. These 4 comparison points, which includes the reference point, will help us determine where exactly a point, in what quadrant a point falls, exactly what quadrant. So if we travel just negative pi over 3, that means we'll end up, this one's actually somewhat easy to determine. If we travel just pi over 3, that means we're going to end up like here, maybe. Or actually, it would be like, yeah, something. It means we'll end up in this quadrant right here, because pi over, yeah, I don't understand. So this is negative pi over 2 is, to say this. This is not true. So this is true if and only if I multiply negative by both sides, I get that. If I multiply both sides by 3 or 6, I get 3 pi is greater than 2 pi. That's true. So because this is true, it implies that this inequality is true. That doesn't help me. Why does that not help? Okay, maybe the best way to think about this is to look at absolute values. And then just remember that. So that'll tell us how far we travel along the along the circle, but then the negative sign will tell us which direction. So if we take the absolute value, we have 2 pi over 3. So if you travel, so let's just think about pi over 3. If you travel pi, so pi over 3 is less than pi over 2. So if you travel pi over 3, that means not in the negative direction, you travel, if you travel pi over, so let's say, sorry, pi over 2 in the negative direction, you end up at this point right here, right? This corresponds to negative pi over 2. What this says right here is that if you travel pi over 3, you should end up closer to the reference point because you're not traveling as far from it. So this tells you how far you're traveling. This number right here tells you how far you're traveling from how far you traveled from the reference point. And so it says that if you travel this distance right here, you're going to end up closer to the reference point than if you traveled that distance. Now, imagine everything going in the negative direction. So that's why this point right here roughly will correspond to pi over 3. Now, the absolute value of the number we're interested in is bigger than pi over 3. And it is bigger than pi over 2. So that means we're going to end up somewhere over here or somewhere over here maybe. But we just do if you do the same sort of comparison we did up here, it will show you that this number right here corresponds to this quadrant, the third quadrant right here. So now we have these two distances, and let's just mark them. So we have this distance right here, and then we have this distance right here. And clearly the length of this red arc is shorter than the length of the blue arc. So that will tell us that the length of the red arc is our reference number. So then T bar will be pi minus 2 pi over 3. And that's going to just be pi over 3. So that will be the reference number right there. So that's all I'm going to do for today. And we'll have some more videos coming next week.